The ability to design appropriate classes may be the single most important skill in object-oriented programming. Classes allow us to encapsulate data relationships in ways that match up very nicely with many real-world problems. But how well your program works, and indeed whether it works at all, can depend crucially on how your classes and their operations have been set up at the start of the program. What's the difference between an optimist, a pessimist, and a programmer? Well, an optimist says the glass is half full. A pessimist says it's half empty. But the programmer says the glass is twice as big as it needs to be. And there's a serious point here. How you define classes makes a big difference. So in this lecture, we'll explore two key tools for getting classes off to a strong start for any object-oriented program. First, constructors, which let us set up our classes however we want, and in particular, ensure that every object we create starts out with reasonable values. And second, operator overloading, which lets us redefine operations on classes however we want. First, constructors. Whenever we declare a new class or object, the computer sets aside a chunk of memory. And this memory will hold all of the member variables for that object. So, we want to have some way of initializing the memory, that is, the member variables, and that's where a constructor comes in. A constructor is a special function run at the time that a new object is created. And its purpose is to initialize the object to some valid state, so that the member variables all have reasonable values. In fact, in order to ensure that our objects begin in valid states, we should always provide constructors for all of our classes. Often, the constructor that we'll want to define is what's known as the default constructor. Now that may sound confusing, but the word default can have two meanings, so it's important to know what's meant here. The default constructor that we're discussing here is what's called when we declare an object in the common way, where we just list the type and then the variable name. But if a user doesn't specify any constructor at all, then the compiler will automatically create its own default constructor for the class. You could say it's the default behind the default. Anyway, a default constructor that you create should be defined as a public member function of the class. We make sure that we write public colon before defining the constructor. The constructor is a special function. There's no return type since the only thing it's doing is initializing an object. The name of the constructor function should just be the class name. Yeah, that's right. The function has a name, which is just the class name. So, for example, in the previous lecture, we defined a class called vending machine, and we would use that same name for our default constructor function. And the default constructor should take no parameters. So, we'll define the default constructor by writing the class name, then parentheses, then inside curly braces, we'll write whatever we want to happen each time that we create a new instance of that class. For example, here's the vending machine example I used in the previous lecture. For clarity, I've eliminated most of the member functions that we had last time, though I've kept an accessor function around so that we can see the results easily. Notice that I've added a default constructor and it comes after the public designation so that it's publicly available. The next line after public uses the class name vending machine as the name for our constructor function. Vending machine followed by parentheses, in this case with nothing inside, then an opening curly brace. Inside of the curly braces, we have all the default values that we want to set for the price, credit, money collected, all of which start at 0. We set the inventory level to a default level of 100. Also, we'll output a message that we've created a new vending machine whenever this constructor is run. Now, down in our main program, look what happens when we declare a new vending machine object named lobby machine. When we declare the new object, there's memory set aside for that object, basically enough memory to contain all the member variables for a vending machine. And notice, the default constructor is now run automatically from the constructor we defined for the entire vending machine class. So, the default constructor will set the price, credit, money collected, and inventory level for that machine. And we'll get output of the line that we've created a new vending machine. If we also access the inventory level using the number remaining accessor function, we see that indeed there are 100 items in the machine. The constructor was what set that value to 100. Now, using a constructor is the preferred way to initialize member variables. First, a constructor is more explicit about what's being done at the time of declaration. And second, a constructor is far more flexible. A constructor can print out a message, as in the example we just saw. It can also perform more complex calculations, including making function calls, or forming more complex variables like vectors or other objects, and so on. The constructor format is very much like a function, but without a return type. We can even take parameters in for a non-default constructor, just like we take in parameters for a regular function. Then, when declaring a new object, we include parentheses and arguments. We've seen this before. For instance, when we declare a string, we can give an initial string in parentheses. The string is initialized to have that argument as its string value. And that is, we're invoking a constructor that takes in a string, or more specifically, an array of characters as input. Or when we declare an f stream, we can give the information needed to open the file as parameters. In this case, the constructor takes in a file name and possibly other parameters saying how to use the file. Now, both of these were cases where we invoked a non-default constructor. So, let's look at how we could define a new constructor for our vending machine. Let's say that we wanted to be able to specify a specific starting inventory level rather than the default level at the time that the object's allocated. In that case, we'd want a constructor that takes in one integer parameter. Remember, this is no longer the default constructor, the one with no parameters, but rather a new constructor. Again, the name is just the class name, but now it takes in a single integer, starting inventory. And the function itself sets up all the other values to their defaults, but sets the inventory to that parameter value that should be passed in. When declaring a new vending machine, we give the variable name, which in this case is again lobby machine, but also have parentheses in which we have a single integer argument. Then when we run this program, the new constructor, not the default constructor, will be used to initialize the object. So in this case, since we passed in 50 as an argument when we declared the vending machine, we have an initial inventory level of 50. Notice that we can pass in arguments that are variables just as easily as other values. In this case, we read in from the user a number of initial items that the machine should be stocked with. Then we declare a vending machine with that number. And notice that this sort of initialization could not occur if variables were just set to default values by assignment statements in the class declaration. Let's try a slightly different example. See if you can write a constructor that takes in both an item price and an initial level of inventory, and then call that to create a vending machine that has 75 items costing $5 a piece. Here's one way to implement that. We create a constructor with two parameters inside the parentheses, a floating point number for the price and an integer for the inventory. Then the constructor uses those parameters to initialize price and inventory. It sets the other values, and then it prints a message stating the number and the price of items. Our declaration is just a line where we declare a vending machine and pass in the numbers 50.0 and 75. Because we're giving floating point and integer arguments, the non-default constructor that takes floating point and integer parameters is the one used, and it sets the values appropriately. Now, one thing that might trip you up is that you should not try to declare an object using the default constructor by just using parentheses with no arguments. That's the way we declared a constructor within the class, so why shouldn't we call a constructor the same way? Well, look at this line of code, which is not what we want. We have vending machine, space, lobby machine, parentheses, and a semicolon. Now, does that look like anything else that we've already seen? Well, that's the way that we would declare a function. In this case, we might think that we're declaring a vending machine object named lobby machine using the default constructor, but that's not correct. Instead, what this line of code does is it declares a function named lobby machine that takes in no parameters and returns a vending machine. And that's not what we want at all. So be careful. If you're using the default constructor, just leave off the parentheses entirely. Only use parentheses when you want to use a non-default constructor, or when you're declaring the constructor within the class. The point to remember for now is that constructors are a useful way of helping us ensure that our objects are initialized correctly. Now, let's talk about a different way that we can improve on the classes we've defined, and that's by operator overloading. We already saw function overloading, where we can use the same function name, but take different parameters to get different behavior. And this will be similar, but we're going to take different operands to get different behavior from an operator. Now, we've already used examples of operator overloading. We've seen how the plus sign can be used to mean addition for number types, or concatenation for string types. The operator has been overloaded to take on more than just one meaning. It has different meanings depending on the implementation. But that's not the only place that we've had operator overloading. Take the streaming operators, for instance. These are the double greater than or double less than signs used for streaming input and output, either for the console or a file or for a string stream. The streaming operators have been defined for multiple data types. When we have the stream operator to output a floating point number, it will behave one way. It analyzes the number and it displays the digits of the number with the decimal point shown in the correct position. When we use the same streaming operator to output a string, it behaves a different way. It analyzes the array of characters kept in the string, and it outputs each character in the string to the stream. Using stream operators to stream from input shows the same differences. The input is treated in a way specific to the type that you're wanting to read in. So, we can use the same operator, the stream operator, but it is specialized to the type that we need. In fact, the stream operator can also be used with an integer on the left, where it has a totally different operation from when there's a stream on the left. With integers, the stream operator actually means shift the bits of the integer left or right a certain number of spaces. Now, while those bit shifts can be useful in making really efficient code, that operation has nothing to do with streaming input or output. Now, imagine if we did not have operator overloading. We would have to have different operators for outputting integers, outputting floats, outputting strings, and so on. And streams aren't the only overloaded operator. Think of comparisons, the greater than and less than operations. It makes sense what greater than and less than mean in terms of numbers, but we also use them to compare strings. In the case of strings, this gives us strings in alphabetical order. And since comparisons are the basis for algorithms like sorting, overloading comparison operations lets us sort a vector of strings or anything else, just like we would sort a vector of numbers. The point here is that operator overloading is more than just a clever way to put familiar characters to a new use. It can be a fundamental part of making a class more widely usable. There are a wide variety of operators that we can overload. We have binary operators, which take 2 elements per operator. So examples of this range from the arithmetic operators, addition, subtraction, multiplication, division, and the remainder operator, written with a percentage sign. Streaming is a binary operation. There are comparisons like greater than or not equal. And there are Boolean operators like double ampersand for and, or double vertical bars for or. And there are also a few unary operators, operators that take just a single element. So these include the minus sign, or the plus plus, or the exclamation point, which is often used as a logical not operator. All these operators, and even a few less common ones, are operators that we can actually overload. We can create our own version of how they should operate for a particular class or a combination of classes. For example, we could define division between two vending machines to mean take the average inventory level of the items between the machines. That's at least kind of like dividing the product between the two machines, even if it has nothing to do with the divide we use in arithmetic. Let's look at one way of overloading a binary operator, where we define an operator very similar to the way we define a function. Whenever a binary operator is used, there are going to be two operands, one just before the operator and one immediately afterward. Then there will be a result of some type. So, for instance, a comparison operator should probably give a true-false Boolean result. The type of result is basically the return type of the operator function. The function will take exactly two parameters, and these will be the object type of the first and second operands. The only different part is the function name, which will have the keyword operator followed by the particular operation. And all of this gets defined just like any other function would, not as a part of any class. So let's look at an example. Say we have a class that we're using to keep track of light bulbs. Every bulb will have three pieces of data: the number of watts used, the number of lumens, that's the amount of light produced, and the equivalent color temperature of the bulb. And we can define a class with those member variables, as you see here. Notice that all three member variables are public in this case, and that a default constructor is being used to set initial values for the three values. Let's say that we want the ability to create a new bulb that's some factor multiple of an existing bulb. For instance, if a bulb is 2 times another bulb, it should use 2 times as many watts and produce 2 times as many lumens, but have the same color temperature. Let's see how we could define a multiplication operator for the light bulb. Our multiplication operator should take in two operands, a light bulb and an integer that we're multiplying the light bulb by. And the result should be a new light bulb, one using that factor more watts and producing that factor more lumens. So our operator definition should produce another light bulb as a result. So the definition has a return type of light bulb. So we would then write operator space asterisk, showing that we're defining the multiplication operator. Then the parameters for the operator should be a light bulb, which I've labeled bulb in this case, and an integer, which I've labeled increase factor. Inside the function, notice that we create a new light bulb that I called ans, short for answer, since it will be the answer that we return from the operator. We set the watts used and the lumens as a product of those elements of bulb multiplied by increase factor. And the color temperature is just the same as bulb is. Then we return ans. In our main routine, we can now create two bulbs named bulb A and bulb B, where bulb A is initialized with the default constructor so that it has 60 watts, 900 lumens, and a 2700 color temperature. And we set bulb B to be bulb A times 2. This will call the multiplication operator on a light bulb times an integer. So bulb B should have twice the number of watts, or 120, and twice the number of lumens, or 1800, while having the same color temperature, 2700, as bulb A. And sure enough, that's what we see as a result. Now, one thing to note is that operators are not automatically commutative. In other words, we cannot switch around the order of the two operands. So we could not multiply an integer times a light bulb. We defined light bulb times integer, but not the other way around. If we also wanted to be able to define an integer times a light bulb, we'd have had to define a separate operator. And then we could multiply 2 times the light bulb. Now also, if we had not made the member elements public, then we couldn't have written the multiplication operator. It wouldn't have been possible to access the private member variables of the object from outside the function. Instead, we'd have had a compilation error. So, it's more common for operators to be defined within a class. That way, we can access all the elements of the class without accessors and mutators. Let's see an example. In this case, I've made the member values private, but I've added a printVals function that prints all the member variables to the console, separated by spaces. And this will let us print the values of the member variables from outside the class. The main routine is set up to be very similar to before, with the only difference being that I'm calling the printVals function since the member variables of the lightbulb class are now private. Now, notice how I've defined the multiplication operator inside the class. First, we still have the return type of lightbulb, just like we did when the operator was defined outside the class. We also still have the keyword operator and the particular operator we're dealing with, which in this case is the asterisk for multiplication. A key difference to note is that there's only one parameter, an integer. The first parameter, in this case a light bulb, is implied because this operator is being defined inside the light bulb class. When defining in a class like this, we don't specify the first parameter, and we'll get an error if we try to. Now, inside of the routine, we can access the values of the member variables for the particular light bulb we're operating with directly. We simply write watts used, lumens, and temperature to get the watts used, the temperature, and the lumens for this particular light bulb. And notice that I could set the values for the member variables of the light bulb I'm returning directly. Even though they're private members, since I'm writing this routine inside of the light bulb class, I have access to all of those member variables, even the private ones. Also, keep in mind that the order of operations still matters. By defining multiplication inside of the class, that only helps us multiply a light bulb by an integer. We still could not reverse that to multiply an integer times a light bulb. In fact, from within the light bulb class, you have to start with a light bulb, multiplied times something. From within the class, we can't ever do the reverse. We can't define something times a light bulb. The only way to define something times a light bulb would be to define it outside the class. Now, we've seen some examples of binary operations, so let's look at unary operations. Let's try defining a new operation for the exclamation point, which usually means not in Boolean logic. Remember that we can define operators to mean whatever we want, and the best redefinitions typically expand an existing meaning in some way. So here, let's say that the exclamation point defines a dead light bulb, literally a not light bulb. We'll set the watts used and the lumens to 0, and we'll copy over the color temperature from before so we can remember what each was originally. Now, some non-incandescent bulbs actually draw a little power even when they don't produce light, but we'll ignore that here. If we define our unary operator inside the class, we have an empty parameter list. We just write light bulb, operator, exclamation point, parentheses. The function definition just sets watts used and lumens to 0 and copies the temperature member variable. In our main routine then, we can create a light bulb named bulb, then print out the values from exclamation point bulb. And we see that indeed we have the modified value. So, in the example you see here, we've created two versions of the plus plus operator. One for prefix and one for postfix. We have an elephant class with height and weight. The prefix operator will increase the height of the elephant, while the postfix operator will increase the weight. For the prefix operator, we just have the operator defined with no parameters. For the postfix operator, we have an integer parameter included. That integer parameter never gets used. Now, if we were to define the operator outside the class, then the prefix version would have one parameter, of type elephant in this case, and the postfix version would have two parameters, the first one being an elephant and the second one being an integer. One of the main advantages of defining a function or operator inside a class is that you get access to member variables and functions. But even if you define functions or operators outside a class, for instance, because the function or operator involves two different classes, there's actually a mechanism to make a function or operator still get access to the member variables. And this is by declaring the function or the operator a friend. To do this, you include the function or the operator signature in the class definition with the designator friend. And that way, you can define the function outside the class and still have access to member variables. Here's an example using our light bulb multiplication. In the class definition, we say there's going to be a friend operator that will multiply a light bulb times an int. The way we do this is to write friend light bulb operator asterisk parenthesis light bulb comma int parenthesis semicolon. Notice that we don't need to give the parameter names, just the types. Then, outside of our class, we can define the actual operator, this time with named parameters. And because this is a friend function of the lightbulb class, it will have access to all the private members of the lightbulb class. So, if our lightbulb has the parameter name bulb, we can access elements of the lightbulb by writing bulb.lumens and so forth. We can also assign values to objects of the type lightbulb by writing and assigning things like ants.temperature, where ants is a lightbulb object. Now, someone always asks where it's best to define operators, inside the class or outside. And it's a good question, but there's no single right answer. So I'll give a couple rules of thumb. It usually makes sense to define an operator inside the class if you're defining any unary operator, or a binary operator that operates on two of the same type, like a comparison of two objects of the same class. Why? Because these are operations that are a part of only that class and no other. On the other hand, it can make sense to define outside the class if two different classes are involved, and especially if you need to provide an operation in both forms, like car plus driver and driver plus car. Here, the operation doesn't really belong to either class, so it makes sense for it to be outside of both of them. Now still, these are not hard and fast rules. It's more of a judgment call. Think about whether an operator feels more like it's part of a class or whether it feels more like it's external to the class. Let me finish up by returning to one of the most useful operators to overload, the stream operator. It's very common that we'd want to stream data from an object to output it to the console, to a file, or to a string. And likewise, it's common that we'd want to stream data into an object. It would be nice to declare a lightbulb object and just be able to see out that lightbulb, or see in the lightbulb. But to do this, we have to overload the stream operations. Now, remember, the syntax of a stream operation is we have the stream on the left, then the stream operator, either double less than for output or double greater than for input, then the thing that we're wanting to stream out of or into. And the stream should be able to continue afterward. Since the stream itself comes at the left of the list, that means that we can't write a stream operation for our new class as part of the class. So instead, we need to have the stream operation defined outside the class. It's a good idea to make this stream operator a friend operator, since that way we'll have access to the member variables. To have a sense of what we're doing, you can think, if I'm outputting to a stream, I will have an O stream, and if I'm inputting, I'll have an I stream. Both I stream and O stream are predefined stream types, where CIN is an example of an I stream, and cout is an example of an O stream. We'll also need to make sure that our operator returns another stream, since that way we can stream one thing after another. The result of the operation is a stream, which can then have another stream operation applied, and another, and so on. Let's look at a quick illustration with the light bulb. Say we want to output 3 member variables: watts used, lumens, and temperature, separated by spaces. Then, anytime we want to stream output, we can then just stream a light bulb, and we'll have that information printed. No need to call print vals or anything like that. So in the example here, we will, inside of the lightbulb class, declare a friend operator. Notice that the stream operator will take in first an OStream reference and a constant lightbulb reference in the parameter list. Also, notice that the return type is an OStream. The result still needs to be a stream so that we can continue streaming more stuff. Now, outside of the class, we can actually define this stream operator. In this case, I've given the stream parameter the name S for stream, and the lightbulb parameter the name B for bulb. So, I just stream out to S the 3 elements of bulb B, separated by spaces. Notice that because it's a friend function, I can access the members of B directly. The stream operator should return a reference to a stream. That's how the streaming can continue. The result of the stream operator is another stream that then becomes the left side of the next stream operator, and so on. So, in the definition of the operator, I just return S. The key thing to notice is that now we can stream our own class out just as easily as we've been streaming out integers, floats, and strings. Constructors and redefined operators make classes and objects more useful. Constructors help us initialize objects, making sure that all the member variables have valid and consistent data. Operators we redefine help us use classes more effectively, such as being able to stream classes directly to output. In the next lecture, we'll see when to use an object-oriented technique that's kind of the opposite of a constructor, the destructor. And that will involve looking a little deeper at what's really going on when we allocate memory, and learning some new ways of allocating memory ourselves. See you then.